Hi class, nice to see you again. Today we move to the third lesson in the series of the English of the thermal engineering subjects, and the title of this lesson is the basics of the heat transfer. And of course you are the thermal engineering students, so for you is thermodynamics and heat transfer. You relearned it in Vietnamese, and as I mentioned in the first lesson, thermodynamics and heat transfer is two core, or I can say it's most important subjects that you need to familiar in order to explain everything related to your engineering area. You already learned this in Vietnamese, and now you learn it in English, and I hope that English version will help you to summarize everything you learned in Vietnamese. Okay, like usual, before we start the lesson, I would like you to get familiar with the old vocabularies in the lesson. Now, listen and repeat after me. Conduction, conduction, convection, convection, radiation, radiation, mechanism, mechanism, simultaneous, simultaneous, heat exchanger, heat exchanger, adjacent, adjacent, vibration, vibration, energetic, energetic, transmit, transmit, particle, particle, molecule, molecule, cohesive, cohesive, natural convection, natural convection, forced convection, forced convection, thermal resistant, thermal resistant, thermal radiation, thermal radiation, heat transfer coefficient, heat transfer coefficient, electromagnetic, electromagnetic, electromagnetic wave, electromagnetic wave, emissivity, emissivity, shell and tooth heat exchanger, shell and tooth heat exchanger, plate heat exchange, plate heat exchanger, in series, in series, in parallel, in parallel, multi-tube heat exchanger, multi-tube heat exchanger. Okay, so now there are 6 main parts in this lesson. First is introduction, second, the conduction, third is the convection, number 4 is radiation, number 5 is a simultaneous heat exchange mechanism, and number 6 we go through some heat exchanger. Alright, why we need to have a good knowledge of the heat transfer? You know, the heat transfer provides basic background to understand how thermal system work. You know, the thermal system is the object of your engineering area. For example, the heat engine, like diesel heat engine, the jet heat engine, or air conditioner system refrigerator, or the dryers, boilers, pump compressor, or the system like a solar system, for example. So you see that all this thermal system will have one to another form of the heat transfer. So that's why you need to understand very clearly the heat transfer in order to know this system well. So heat transfer plays major roles designed for many devices, from the radiator of your motorbike or the car, for the solar collectors, various components of the power plants, or even spacecraft, etc. So is all this related to heat transfer. So when you know well about heat transfer, you can design this component or this device as well. So, you know, the heat transfer is due to temperature difference. You know that when there are two objects put next together, or we call adjacent, and they have different temperature. So there will be the heat transfer from the body have high temperature to the lower temperature body. So we call that procedure is the heat transfer. Look at the picture again. You got the hot cup coffee, and because the hot cup coffee have degrees around say 70 degrees, while the temperature is about 25 or 30 degrees. So definitely there will be the heat transfer from the hot coffee cup to surrounding. So we call that the heat transfer procedure. On the next picture, when you use the bare foot, stand in the ground, and this ground is, you know, exposed to the sun for a long time, so you know the ground become hot. So when your bare foot is contact with the ground, your foot will feel hot. It is because the heat is transferred from the hot ground to your bare foot, so you feel hot. That is kind of heat transfer, and again, that's because of the different temperature between the hot ground and your your bare foot. And this one, the heat transfer, that is the heat energy. And again, you know that all kind of energy, we have the unit either joule or the watt. Watt is the joule per second. So the problem of the heat transfer is to determine the temperature at a certain position and determine the amount of the heat flow through an object. You learn in heat transfer, and you know there are three. If we separate them, there will be three main heat transfer mechanisms. That's called the conduction, convection, and the thermal radiation. The conduction, it means when the transfer of energy or transfer of heat arising from the temperature differences between adjacent parts of the body. Okay, so for example, look at the picture. We got the pan egg, and because the you know, when you use the fire to heat up the fan, and the fan, it just transfer the heat to the egg through the fan, and this one we call the conduction. The convection is a mode of energy transfer between a solid surface and the adjacent liquid or gas that it is motion. Okay, you know, convection is related to something move. We call the motion. Okay, so this one, if we say the conduction is purely for transfer heat through the solid body, so the convection is a transfer from a solid object to surrounding, and normally surrounding will be either liquid or the gas. And again, look at a picture of the hot egg. You know, when you put the hot egg outside the surrounding, the hot egg will be cooled down. How can it be cooled down? Because first the air surround the hot eggs become hot, and its density is become less, and it just move up, and the air surrounding just occupy the space of the hot air. It make the circle, or they make the air motion. So in this case, it make the convection. And in this case, because you just let the air just move it naturally, so we call it the natural convection. In the next picture, to cool the hot eggs faster, you can put the fan, and you see when the fan you put in, the air will be moved faster, so the heat transfer coefficient will increase, so it helps to release the heat from the hot egg faster. So this one we call the forced convection. The third kind of the heat transfer mechanism is a thermal radiation. So you see that if the conduction, they need the solid materials. For the convection, they need the liquid or the gas materials. For the thermal radiation, they don't need either the solid or nor liquid nor gas. In other words, the mode of the heat transfer in the form of electromagnetic radiation at the speed of light, we call the thermal radiation. For example, as you know that the sun, they just release the radiation to the earth. And you know, between the sun and the earth, there is no kind of materials between them. So it means the sun is released the radiation, the thermal radiation, through the electromagnetic waves to the earth and heat up the earth. So that is the thermal radiation. And this picture shows you that normally there's not one kind of heat transfer mechanism, but normally is the combination of the two or even three kind of heat transfer. Look at this example. The fire, they release the heat, or they transfer the heat through the radiation, and then when it touched the pot, the water in the pot, it just make the movement, and it will transfer from the bottom to the top by the convection. And if you use your hand to touch the pot, your hand will feel hot because the conduction from the hot pot to your hand. So now we go in the detail of these three kind of mechanism, heat transfer mechanism. First is the conduction. This form of heat transfer can happen in solid, liquid, gases, but more popular in the solid. The mechanism of the conduction in solids is the combination of vibrations of the molecules in the lattice and the energy transport by the free electrons. Look at the picture in the screen. You can see that the molecules in the solid, there are many molecules inside, when the liquid is less and gas even lesser. So the conduction is the transfer of energy from more energetic particles of the substance to the adjacent less energetic ones. So why metal are good thermal conductors? You look at the picture there. There are the decollized electrons, or we call the free electrons in metal. There's many of them. So these free electrons can move freely throughout the metal. When heated, these free electrons gain kinetic energy and move from the hotter end to the colder end, carrying energy with them. This process is much faster than the conduction by the vibration of the molecules. So you see that's because the electrons move freely. So in the metal, it can be the good thermal conductor. In other words, materials that can conduct the electricity good is also conduct the thermal good. All right. So the conduction is a process by which heat is transmitted through the medium from one particle to another. You look at the picture there, you can see that when the particle or the electron hit directly by the sun, it gains the energy and start to vibrate more vigorously. So the next particles are pushed and pulled about by their vibrating neighbors, so that they start to vibrate faster too. And finally, eventually, the particle at the end, far end of the rod, are made to vibrate vigorously. The end of the rod gets hot. So that is the procedure of the conduction. And you know that we use the Fourier equation to calculate the amount of the heat conduction heat. You look at the formula, we got Qx equal to minus lambda times F times delta T divided delta X. This one is we use for the area F. In case we consider as just the 1 unit of area is Q small x equal to Qx divided by F equal to minus lambda delta T divided delta X, and units is watt per square meter. So in this equation, Qx is the heat flowed through medium by conduction, and Q small x is the heat flux through medium by conduction. T is temperature is the Kelvin scale. F is gross area that perpendicular with X actual. Lambda is thermal conductivity of the materials. And the next picture, this is about determine the heat transfer through the plane wall by conduction. You see that it is we have a wall with the properties areas is F, the thickness is delta, thermal conductivity is lambda, and temperature of the two phases is T1 and T2. We apply the Fourier law. We got Q equal to lambda times F times delta E divided to delta. And for the unit of area, we got small q equal to delta T divided to delta divided lambda. And you look at this formula, it's similar to the Ohm's watt that you learned in the physics, that I equal to U divided by R. In other words, in these two formula is similar. The Q is similar to I, delta E equal to similar to the voltage, the different voltage U, and delta divided by lambda we call is thermal resistance. It's equivalent to the electrical resistance of the materials R. So it means if we apply the Ohm laws to the conductivity through the plate, we can use the method they call the similar method to apply the Ohm laws to the Fourier's law. Okay, so it means if your walls have the 3 layers with different temperature, different thermal conductivities, and different thickness, so we got the first end in the left have the temperature is T1, and the right end is have temperature is T4. We got the heat transfer by conduction through the multi-layer wall is Q equal to T1 minus T4 divided to R lambda 1 plus R lambda 2 plus R lambda 3. So of course R lambda 1 and R lambda 2, R lambda 3 will be equal to delta 1 divided by lambda 1, delta 2 divided by lambda 2, and delta 3 divided by lambda 3 respectively. Okay? And here's the thermal conductivity of some materials. As you look at this one, you can see that for some materials, like they call it non-metallic crystal, like diamond, graphite, silicon carbide, etc., quartz, they have the very high thermal conductivity. Next is the pure material. We got the silver, we got the copper, iron, etc. So the metal alloy is the combination of different metal, like we got aluminum alloys, bronze steel, nickel alloys have the lower thermal conductivity. And go down, you can see that will be the gas have the very low. So look at this scale, you can see that, for example, if the non-metallic crystal like diamond, graphite, the thermal conductivity is 1,000 watt per meter per degree, whereas the gas only from 0.1 to 0.01 watt per meter per degree. So that means it's just 1,000,000% compared to the diamond crystal. And here is just the value of someone. For example, diamond is up to 2,300, copper is about 400, while air is just 0.0224. So it means that depends on whether you need the heat transfer through the materials is good, or you don't want the heat transfer. For example, if you want to make the heat exchanger, definitely you need to use the metal like the copper or the silver or aluminum or iron to make it. Whereas if you want to isolate the space, you will use isolated. For example, you use good or the soft rubber, etc. Urethane have the very low thermal conductivity to isolate the heat transfer. So the thermal conductivity in solid, if you stir the hot tea using the metal spoon, you will observe that the handle of the spoon become warm. The solids that are good conductor of heat, metal, use both atom vibration and the free electrons to conduct heat. And while liquids are poor conductors of heat, this is because there are large intermolecular distance between liquids and liquid molecules. There are also fewer or rare collisions between the molecules. Electrolyte, as an example, the salts solution are better conductors of heat than the pure liquid because of an increased compactness of the particles. So the thermal conductivities of the gas are the worst conductors of the heat because, again, of large of the intermolecular distance. You can see in the very first picture, you can say that for the solid, because the molecules or the particle is very close, so it can conduct better, while the gas is just very few particles. So you can see that the interaction between them is really bad. So a result of that is the conduction by liquid or the gas is very low. All right, so now we go to the second heat transfer mechanism we call the convection. Convection is a mode of energy transfer between a solid surface to the adjacent liquid and a gas that in a motion, and it involves the combined effect of the conduction and the fluid motion. Again, you look at the picture here, you can see that, for example, we got a cold soda bottle. It will be warm up when it's receive the heat transfer from the surrounding atmosphere, or the hot eggs will be cooled down when it transfers the heat to surrounding air, or the liquid or the water you boil in the pot. Later on, the whole liquid it just warming up or heating up just because it's create a convection. So these three pictures show the first kind of convection we call the natural convection. So what happened to the particles in the liquid or the gas when you heat them? Convection is a mode of energy transfer between a solid surface and adjacent liquid or gas in motion, and it involves combined effect of the conduction and the fluid motion. Okay, so you see the conduction and the fluid motion. The faster the fluid motion, the greater the convection heat transfer. So the convection is a process by which heat is transmitted from one place to another by the movement of the heated particles of the gas and the liquid. Look at the picture here. You see that the gas or the air is near to the fires. It becomes less condensed, or the density is lower and it's moved up. So the surrounding with larger density is will occupy the space. So we make the movement, and then the energy is converted through surrounding. So the convection is a process by which the heat is transferred to fluid. Fluid here this is common name of liquids and gases. When a liquid is heated, it expands, and this lowers its density, as I just explained. The less dense liquid rises, and its place is taken by more dense colder liquid. This movement of liquid forms the convection current. So molecules in fluid are further apart and have a negligible cohesive force. And convection currents are set up much faster in gas than in liquid, because the extremely low cohesive forces exist between the molecules of the gas. Okay, as I already explained, there are two kinds of the convection. We call the natural convection and the forced convection. So the natural convection occurs whenever heat flows between the solid and the fluid, or between the fluid layers. As a result of the heat exchange, change in density of the effective fluid layer taking place, which causes upward flow of the heated fluid. If this motion is associated with the heat transfer mechanism only, then is it called the natural convection. Forced convection, mixing of the hot and the cold part of the fluid through some external stirring, like a fan or the pump. If this motion is associated with mechanical means such as pumps, gravities, or fans, the movement of the fluid is enforced. And in this case, we then speak of the forced convection. Example of the heat transfer by convection. Look at the first example. During the day, the sun heats the land much faster than the sea. The air above the land is heating, expands and rises. Cold air from the sea moves inland to take its place. Hence, sea breeze is obtained. That is in the daytime. In the nighttime, land loses heat faster than the sea. Hot air above the sea, which is less dense, expands and rises. Cold air from the land moves towards the sea, and convection currents is formed, and land breeze is obtained. Okay, so that is you see that is the natural convection. It's caused by the different mechanism of the heat of the land and the sea. And another example, like the air receives and releases heat when flows through the condenser evaporator by convection. And if we use the Fourier laws to calculate the heat transfer by the conduction, we will use the Newton laws to calculate the rate of the heat transfer by the convection. So we got Q equal to alpha F TW minus TF, or for one unit of area, we got small q equal to delta T divided by 1 over alpha. Alpha is the convection coefficient, and this we obtain by the experimental. And F is the surface areas through which the convection heat transfer takes place. And TW is the surface temperature, and TF the average temperature of the fluid. And again, if we call 1 over alpha is alpha is a thermal resistance, we can rewrite the Newton formula in the form of the Ohm law, and we can apply the Ohm law for this case. And the heat transfer coefficients of some materials, and here you can recognize that for our normal materials, because most of the materials for the heat transfer we use in Vietnam here is written by the the lecturer and professor who study in the former Soviet Union, so they use alpha for the heat transfer coefficient. When most of the materials, if we use from the Western countries, they will use the simple H to define the heat transfer coefficient. And again here you can see that for the free convection gas is have very low heat transfer coefficient. For example, the H here is just only from 2 to 25. For the liquid, it's from 10 to the 1,000. If you force the air, that means you got the forced convection, the efficiency of the gas increased about 10 times, up to 25 to 250. And the liquid, it go up to 50 to 20,000. For the boiler and condensation, the heat transfer coefficient up to 2,500 to 100,000, so it's increased a lot. Now, the third form of the third form of the heat transfer, we call radiation heat transfer. The thermal radiation is the energy emitted by the matter in the form of electromagnetic waves or the photons as a result of the change in the electronics configurations of the atoms or the molecules due to their temperature. So if an object receives or releases heat from another by observing or emitting thermal radiation, it can be claimed as exchange energy by thermal radiation. So for the thermal radiation, everything emits thermal radiation, observe thermal radiation from other. I mean, you do these two procedures simultaneously. I mean, we both emit and observe the thermal radiation. The amount of energy emitted from the objects is proportional to the absolute temperature of the power of 4. So we got the Q emit equal to epsilon like time delta like sigma and AS time T power 4. The thermal radiation emitted from the surface of the black body greater than that the surface of the bright body. And here some misses, and we epsilon is we call the admissivity of some materials. Here's admissivity of some materials, and this one you will learn in the heat transfer. So to calculate the amount of the radiation heat transfer, we will use the Stefan-Boltzmann law. And the Stefan-Boltzmann law is, they got formula is Q equal to F12 times F times sigma T1 power 4 minus T2 power 4. In this equation, F12 as admissivity factor, F is the heat transfer area, sigma is the Stefan-Boltzmann constant, and T1, T2 at absolute temperature of two object surface. Okay, that is the three separate mechanisms: is conduction, is convection, and radiation. And in reality, normally there's not the single one of the heat transfer mechanism. It exists, but normally it's the combine of the different kind of heat transfer. So we call that is this simultaneous heat transfer. Look at an example here. For example, we got the wall. The wall is separate between the outside temperature and the inside room. And the outside temperature, of course, is hotter than the inside. For example, inside we have the air conditioner. So in this case, the heat transfer will transfer from outside to inside. And from outside, you can see that it's through the convection and radiation. It will transfer the heat from surrounding atmosphere to the outside of the wall. And then through the conduction, the heat will be transferred from outside hot wall to the inside cold wall. And after that, through the convection and radiation, the heat will be transferred into the room. So you can see that in this case, there is a three combination of the heat transfer mechanism as once. So we call that simultaneous heat transfer. Another example, like if we put the hand near the bowl, the light bowl, you can see that through the convection and radiation, the heat will be released from the light bowl. All right, so now we go to the last section. This is about the heat exchanger. So you know, heat exchanger is the equipment used to transfer the heat. For example, in the air conditioning system, you got the condenser, the evaporator. That is the heat exchanger. So in this lesson, I just introduce you the three main kind of heat exchanger. First, we call the shell and tube heat exchanger. So look at the picture here. We got the two materials. One go into the tube, and one it go to the shell. Look at the picture. We got the inlet tube go into the tube, and then it's go out. The shell is another material. The rate of the heat exchange in the heat exchanger, the inlet and outlet temperature of the hot and the cool fluid, the flow rate of the hot and cool fluid, heat exchanger area, overall heat transfer coefficient, and the cost of the equipment. That is all the parameters that you need to work out when you design a heat exchanger. The second type of the heat exchanger we call the plate heat exchanger. Look at the picture here. You see, instead of using the tube, and the tube, as you know, that it will occupy a lot of space. In this case, they use a plate. So the plate, you know, that is a flat plate, so you can put each next to each other. So you can save the space a lot, and you can increase the heat exchanging areas. So this plate heat exchanger become very popular nowadays. And for the plate heat exchanger, they can put it all channel in parallel. Look at the picture here. You can see they put in the parallel. So the advantage of the parallel one is to have the low pressure drop, but disadvantage is the low heat transfer. Either put in the parallel, they can put in the series. Look at the picture here. There's the 4 plates and they put them in the parallel. So the advantage of the plate heat exchange in series is the high heat exchange, but disadvantage is the high pressure drop. So to combine this advantage and just eliminate the disadvantage of the series and the parallel one, they combine series and parallel. So in this case, you can see they put both in the parallel and in the series at the same time. So in this heat exchanger, the advantage is optimize the pressure drop and the heat exchanger. The plate heat exchanger, normally they use to regenerate the energy. Regenerate here, that means the heat in the hot pasteurized products is used to preheat cold raw products. So for example, you use it in the milk factory. You know that the milk factory, you have to heat up the milk to pasteurize it. So when you hot up, the milk become very hot. So instead of just release the heat to the atmosphere, in this case they put through the plate heat exchanger, and the hot pasteurized products will release the heat to the cold pasteurized products and will heat up the cold products. So this divide they call the generator. That in this case they can bring the efficiency of the equipment up to 90%. It's very high. So the third kind of heat exchanger we call the multi pipe. First is a double pipe heat exchanger. They call a pipe or tube the same. For example, you look at this picture, you can see that there's one small tube inside the outside tube. So this one they call a double pipe or double tube heat exchanger. And the next picture, you see that there's the double tube, the triple tube, and the multi-tube heat exchanger. For the double heat or the double tube or double pipe, you see that the heating only from one side. For example, the cold fluid go in the inside tube, so the hot fluid go out. So you can see that it's only heat up at one side. If you use a triple tube, so for example, the outside one you use for the hot, and the inside one is a hot, the middle one is a cold. So you can see that in this case, the cold fluid will be heated up by both sides, inside and the outside. So it can increase the procedure of the heat exchanger. And the last picture is a multi-tubes exchanger. So that is different kind. So in general, you for the heat exchanger, you make sure that the area as small as possible, so you can increase the heat exchange coefficients. All right, so this is the end of the second lesson. And again, after this lesson, I will provide you the materials, and each of you will receive about 2 or 3 pages, and you need to transfer from Vietnamese to English and English to Vietnamese. All the subject related to the heat transfer, and you have to submit to me. Okay, and it's allowed by the school and by the university recently. In April, through the April, you still have to learn online. It means you have to learn and do exercise by online. So good luck for the class. Goodbye.